Welcome to lecture 6, and today we are going to discuss calculus of vectors and tensors. So calculus means we have to differentiate and integrate. So we know how to differentiate and integrate scalars, but now we will learn how to do that with vectors and tensors. Okay, this is from chapter 5. All right. So, three of the very important operators are what is called gradient, then curl, and divergence. Okay, you may have heard about this, but we want to do this on a general tensors. So let us start with gradient, for example. So we have seen for a scalar function, so if you have f and function of just scalar variable x, so the function is scalar and the argument variable is also scalar. So in that case, the gradient of f is simply f prime, the derivative of f with respect to x. But suppose you have a scalar function, but whose argument is a vector. Okay, so it is scalar, but the argument it's a vector. So are you aware of such functions? Can you think of any function which is a scalar function but argument is a vector? One of the divergence. Well, let's get more basic. For example, distance, for example, or the magnitude. So if I say f of x is equal to mod of x, so the argument is a vector, but what comes output, that is just a scalar. So this is one example. There are many more examples, of course. Now, how do I take its gradient? So this is something you may have seen in your first year mathematics course. And we write in column, we say it is del f by del x1, del f by del x2, and del f by del x3. Isn't it? But you see, when you write in column, it is basically a representation of a vector in a particular coordinate system. Okay, so we should now understand that this is just a representation of a vector in this case it would be E1, E2, E3 coordinate system. Now this is the representation. Then what is the vector itself? How do I write that vector itself? So any idea? So basically this quantity over here is a vector. So it is not correct to say that it is equal to. Maybe we should have put here this bracket and said that we want its representation in E1, E2, E3. And then we can equate. So what is that vector itself? What will that be? So the notation for it is, first of all, this inverted triangle with a bar below. We know that with a single bar we always denote vector. So this is how we denote gradient. So this is the symbol for gradient. Okay, and its definition is the following. So it is going to be del f over del xi tensor product ei. Okay, but because you see this thing over here, this is scalar. F is a scalar and xi is also a scalar. So it doesn't make sense to have a tensor product here. So this is not required. So we can simply write this as del f over del xi into ei. Now this is a vector. Whereas this thing here, that's the representation column of the same vector in E1, E2, E3 coordinate system. Okay. Several places you will also see they write it as del little f by del big X. So basically it's the derivative with respect to a vector. So till now we know how to take the derivative with respect to a scalar, but now we are talking about derivative with respect to a vector. So this is also gradient and it's written as derivative with respect to a vector. So do you have any idea how can we take the derivative with respect to a vector? It's a new thing, isn't it? So for example, how do I take derivative with respect to a scalar? So if f is a function of x, scalar variable, then f prime, if you recall the fundamental theorem of calculus, then it is limit epsilon tending to 0 f of x plus epsilon minus f of x divided by epsilon. Okay, this is the fundamental theorem of calculus for derivative. So we have to think of something like that now also when we are taking the derivative with respect to a vector. So it is defined, you can also define it in the following way. So first of all, we will what is called scalarize this vector differentiation. Let us scalarize. I'll tell you what does this mean. So I will think of a function f epsilon, which is, so f epsilon x is equal to f of x plus epsilon into delta x. All right. And then I would simply take the derivative with respect to epsilon. See here, epsilon is a scalar, a small quantity. And x is our variable, and delta x is like the increment in x. Just like here, epsilon is the increment. This is the increment in x. Well, I should, maybe use different symbol so that we are not confused. So maybe let me use here h. It's the same thing, right? So this is increment in h. Sorry, increment in x. So to do differentiation, what we do, we simply increment the argument a little bit and see how it is changing with respect to that increment. So this is that differentiation here. So here we have now f as a function of epsilon, and I want to take the derivative with respect to epsilon. So how will we do it? So let us do it at epsilon equal to 0. So it's a function of epsilon basically. So any idea how should I do it? So
we can take differentiation of f and then the argument, means like chain rule.
So this is going to be f of x plus h okay, I think it's simply, you could also write it as x plus epsilon delta x minus f of x divided by epsilon. Can you see this? So here, I'm simply taking the derivative with respect to epsilon. And I take the limit at epsilon tending to 0. Is that understood to you? I hope that
Previous
Say
the
again?
value of h is
Please repeat, I could not hear.
so the value of h is
Yeah, I mean, please say again. I think you were speaking at the same time. One of you. Pulkit?
Yes, sir. I wanted to ask in the previous step, can you please explain again, like f, why you are putting a subscript as epsilon? Means, do you mean the change in that?
Well, yeah, subscript epsilon just to say that it is now also a function of epsilon. I have changed the function now. I have changed the function. So the original function is f. Now I'm thinking of a different function, f epsilon, which is defined like this. So this is the definition. So f epsilon is a new function. It is not equal to f. It is a new function.
So then why we are using both?
Yes, please.
Why we are using both epsilon also and delta x also? Can't we use only delta x?
Okay. Well, see this delta x here. Okay, it's a good question. So delta x is like a single variable. It's a single variable. Don't think of delta as being an increment. Delta x is itself together a variable. instead of delta x, I could use something else. For example, eta. Or I could say y also. I could use y also. But I used delta x just to give a hint that it is like an increment in x. But in this definition, I could have used, so I could have also defined f epsilon of x as f of x plus epsilon into some variable eta. So here, what we are really doing is we are increasing our x in the direction of eta. We are increasing x in the direction of eta. So think of, for example, a 2D system, 2D plane, and then we have x here. Okay. Now, what is del f by del x1? Okay, I think I have to go to more basic thing. Let me do it more nicely because you guys have asked this question. So let us discuss differentiation of a function of multiple variable. So differentiating function of multiple variables. So for example, if you have a function f of x1, x2, x3, where x1, x2, x3 are basically the three components of the position vector, where x1, x2, x3 are the components of position vector. Okay, so then you can think of del f by del x1, you can think of del f by del x2, you have del f by del x3, right? I think you all are aware of this partial derivatives. If I want to see it geometrically, it means suppose I am at a point x and if I see how this function f is changing as I move along E1, then this is going to give me, as you move along E1, that is going to give you del f by del x1. And you can define it as limit h going to 0, f of x1 plus h, comma x2, comma x3 minus f of x1 divided by h. Isn't it? That's how you do the partial derivative. Similarly, you can think of moving along E2. And when you look at the rate of change of f as you move along E2, then that's del f by del x2. And you can define it as follows. Del f by del x2 is equal to limit h tending to 0, f of x1, comma x2 plus h, comma x3 minus f divided by h, isn't it? And this f is at x1, x2, x3. Are you all with me?
Yes, sir.
Roshan? Can you understand, Roshan?
Yes, sir. I am here.
Okay. So this is how you define partial derivatives. You can similarly see, you don't have to go just along E1, E2, E3. You can in fact go in an arbitrary direction. You can think of going in an arbitrary direction. Let us say you think of it as eta. So any point here, so this point you can define it as x plus eta, so plus epsilon into eta, where epsilon is the distance in this direction and eta is the direction. Okay. So if I want to take the derivative as I move along eta, how will I do it? So that would be, I would say, let us take f of x plus epsilon into eta, okay, minus f of x, and then I take the differentiation with respect to epsilon. Can you see, does it make sense to you? And you see this, you can take this epsilon as h also, doesn't matter. This, so here you have to take limit epsilon going to 0, and this is same as writing it as limit h going to 0, f of x plus h, sorry, plus h into eta minus f of x divided by h. Does anyone have any confusion here? See, I could also write it in component form. Same as limit h going to 0, f of x1 plus h times eta 1, comma x2 plus h times eta 2, comma x3 plus h times eta 3 minus f of x1, comma x2, comma x3 divided by h. So basically here, as I move along eta, I'm changing all the three components, x1, x2, x3. And that's why all the three arguments have changed here. You can see all the three arguments have changed. And they change in a particular ratio, which is given by the component of eta. Eta 1, eta 2, eta 3. Okay, this is also called directional derivative. Along eta. Okay, now you please tell me what were you asking, Niranjana?
Sir, what is epsilon defined? Like that is a distance between which points or something?
Please again, what is?
What is epsilon like geometrically? Like you have denoted it as.
So as you can see here, you see here what is epsilon. Can you see this epsilon?
That's like origin of this E1, E2 and the distance.
Like the distance that I have traveled in the direction of eta.
From this origin, right? E1, E2.
From not from origin, from the point x, where we want to take the derivative. See, the origin is here. This is the origin.
Okay.
But I am taking from the point x, because whenever you take the derivative, you have to move from the point at which you want to take the derivative.
Okay, sir. No,
Sir, eta is a direction.
Eta is a direction, yes.
And that is a multiplication of increment and the direction. H and eta.
No, eta is simply here a direction. Why are you saying it is a multiple of increment and direction? It is simply direction.
Okay. Okay, sir.
The total
So means
increment is epsilon into eta or h into eta.
okay. Means h is the increment in direction of eta 1 and other in second term the h is the increment in direction of eta 2 and in the term h is the increment in direction of eta 3. Like
Basically,
this.
h is the increment along eta. So as you do that,
Okay.
then the components in the three direction are then h into eta 1, h into eta 2, and h into eta 3.
Okay, sir.
The h you have, that is the distance on that vector, on that line. H is the distance on this line itself, on this line. Are you able to understand? Please ask me if you are
Sir,
not following. Yeah.
sir, I have a couple of
Yes, sir.
questions. Like,
Yeah.
why you are using two means instead of h eta, you can write only one vector.
Well, I could write one, but then what are you then going to differentiate it with respect to? See, you have to write it in a fashion like this. डिनोमिनेटर में फिर क्या लिखोगे और किसका लिमिट जीरो लोगे?
h eta की जगह एक मान लो कि बीटा लिख दिया और
बीटा
नीचे
लिख
भी
दिया,
बीटा
ठीक।
ही लगा देंगे। अच्छा, मगर वो फिर
नहीं,
वेक्टर हो जाएगा।
हाँ वेक्टर हो जाएगा ना, पता नहीं है ना कि वेक्टर से डिवाइड कैसे करते हैं। यू नो हाउ टू डिवाइड बाय
अच्छा,
वेक्टर?
नहीं वो नहीं आता। ठीक है।
राइट।
और सर ये जो ईटा है, इट इज नॉट यूनिट वेक्टर ना?
Eta need not be a unit vector, yes. It is not
तो
necessary
वाई,
that it is a vector.
ओके, तो व्हाई डोंट वी यूज why don't we standardize eta? Because eta is only giving us the direction. The corresponding
No,
magnitude is given by h, मतलब multiplication।
see, you can also make eta as a unit vector. It is your choice what you want eta to be, but it is not necessary that it's a unit vector. This formula is simply giving you directional derivative along eta.
Okay.
But if you, of course, if you now this directional derivative will be different depending on whether eta is unit vector or eta is not a unit vector. सपोज करो eta को हम लोगों ने यूनिट वेक्टर ना लेके ट्वाइस ऑफ यूनिट वेक्टर ले लिया,
हाँ,
तो फिर एप्सिलॉन एप्सिलॉन को देखो, अगर एप्सिलॉन को सेम अमाउंट से चेंज करेंगे तो हम लोग उस डिस्टेंस में 2 टाइम्स मूव कर जाएंगे. लेट मी
करेक्ट।
रिपीट व्हाट आई जस्ट सेड. So I again have this coordinate system with origin at O, and here is the point X. And let us say I want to move from X along eta. So any point here, which is given by Y, can be written as Y equal to X plus epsilon into eta. So it is the equation of a line in the vector form. It's the equation of a line in the vector form. Y equal to X plus epsilon into eta. सपोज करो दूसरे केस में हम लोग लेते हैं y इक्वल टू एक्स प्लस एप्सिलॉन इंटू ईटा स्टार, वेयर ईटा स्टार इज इक्वल टू 2 टाइम्स ईटा. ठीक है. सो currently let us say eta is of unit vector, eta is 1, and then we have eta star which is equal to 2 times eta. Now let us see what directional derivative is giving us. So in the first case I will say f of x plus epsilon into eta minus f of x divided by epsilon and limit epsilon tending to 0. Okay, In the second case, when I do this, f of x plus epsilon into eta star minus f of x divided by epsilon. So it will turn out that these two are not the same. They are not same. और ऐसा भी नहीं है कि क्योंकि ईटा स्टार यहाँ पे 2 टाइम्स ईटा है तो ये दोनों डेरिवेटिव जो है 2 टाइम्स से रिलेट होगा, ऐसा कुछ नहीं है. The argument is changing twice as fast. That doesn't mean the derivative will also be twice, because the function f need not be linear in its argument. It can be non-linear also. But both are called directional derivative. I hope you got the idea of this directional derivative.
सर वो जो मैं वो पूछ रहा था
हाँ.
बीटा वाला, उसमें बीटा की मैग्नीट्यूड से नहीं डिवाइड कर सकते?
वेल कर सकते हो, हाँ वैसे भी कर सकते हो, बट वैसा करने पे तुम्हारा जो रिजल्ट आएगा वो हमेशा यूनिट वेक्टर के लिए आएगा, फॉर ईटा यूनिट वेक्टर के लिए आएगा. सो व्हाट यू आर सेइंग इज, व्हाई डोंट आई डू द फॉलोइंग, f of x plus beta minus f of x divided by, but इसमें भी एक प्रॉब्लम है, I'll just tell you, divided by mod of beta, and then you say limit mod of beta tending to 0, right? Is that what you're saying?
यही कह रहा हूँ.
Now you see this has got some problem. Can you see what is the problem with this formula? So this is not defined. Anybody can see why it is not defined? Try to think of it from geometry perspective. What is derivative? It is simply the rate of change of a function, right, in a direction in which we are moving. So यहाँ पर देख के क्या लगता है, ये क्या देगा, और क्या ये कुछ एक सिंगल नंबर देगा या कुछ डिफाइंड ही नहीं है ये? एनी आइडिया?
तो देखकर तो लग रहा है कि वेक्टर देना चाहिए, क्योंकि ऊपर वेक्टर है नीचे स्केलर है.
नहीं, ऊपर वेक्टर कहाँ है? ऊपर तो स्केलर ही तो है, f तो स्केलर फंक्शन है ना, f का आर्गुमेंट वेक्टर है, पर उसका आउटपुट तो स्केलर है.
ओके, हाँ मतलब स्केलर अपॉन स्केलर में स्केलर,
स्केलर अपॉन स्केलर स्केलर होता है ना. तो ये बताओ कि ये इज इट वेल डिफाइंड? देखो इसमें क्या लिखा हुआ है कि हमें x को बीटा से इंक्रीमेंट करना है और डिवाइड करना है बीटा के मैग्नीट्यूड से. Now you can do it in several ways. This can be done in several ways. सपोज करो अगर तुम लेते हो बीटा वेक्टर इज इक्वल टू सम एप्सिलॉन इनटू E1, अगर ये लेते हो तो मॉड ऑफ बीटा क्या होगा? एप्सिलॉन होगा. अब देखो, अब यहां पे लगा के देखो कि ये क्या देगा तुमको. इन दैट केस व्हाट इज दिस गोइंग टू गिव यू? Anybody can tell me what will this give me अगर बीटा ये ले लें तो?
बस इवन की डायरेक्शन में चेंज मिलेगा।
सर जो आपका पहला
Even-
इक्वेशन आपने लिखा था
हाँ बोलो।
हाँ सर, जो पहले आपने जो लिखा था सर वही क्वेश्चन मिल जाएगा वापस जैसे कि एप्सिलॉन वहाँ पे एप्सिलॉन का काम करेगा और इवन हमारा जो ईटा का काम करेगा, तो सेम हो जाएगा सर वो तो।
नहीं, सेम पहले का जैसा हो गया, बट एक्चुअली में क्या देगा ये? यू आर राइट कि पहले का जैसा हो जाएगा, बट एक्चुअली में देगा क्या ये? फिजिकली ये क्या बता रहा है? कैन यू से व्हाट इज दिस टेलिंग अस फिजिकली? यस निरंजना, I can't hear. Anybody can tell? Satyendra Prakash Singh.
So, derivative of f with respect to x, like in the even direction.
Oh, who is this guy?
Satyen.
कौन है?
Satyen, sir.
Satyendra, okay. Yeah, so you are right that this is going to give us derivative along E1. So this is del f by del x1. So पुलकित भी ऐसा कुछ बोल रहा था। अब यहीं पे मान सपोज तो चूज करते हैं बीटा इक्वल टू एप्सिलॉन E2, तो देखो मॉड बीटा क्या हो गया, एप्सिलॉन हो गया, तो ये फिर दे देगा del f by del x2। तो इस फॉर्मूला का बेसिकली कोई एक आंसर है ही नहीं, इसलिए ये वेल डिफाइंड नहीं है, एंड देयरफॉर वी कांट डू इट लाइक दिस। ओके पुलकित?
ओके
सर?
मतलब जो स्टैंडर्ड फॉर्मूला नहीं है, मतलब इसमें
एक देखो आवाज ठीक से नहीं आ रहा यार, ठीक से बताओ, बोलो।
मतलब ये स्टैंडर्ड फॉर्मूला नहीं है, मतलब आपका कहना ये है कि बीटा ऐसा नहीं है कि मतलब हर चीज के लिए इसको यूज कर सकते हैं।
समझा नहीं मैं, फिर से बोलो, क्या बोल रहे हो?
सर मैं ये कहना चाहता हूँ कि ये मतलब एक स्टैंडर्ड फॉर्मूला नहीं है कि मतलब सिर्फ वैल्यू पुट करके आंसर आ जाएगा उस फॉर्मूले में। मतलब बीटा जो कि एक फॉर्मूले का पार्ट होना चाहिए था, वो हमें खुद डिफाइन करना पड़ेगा।
हाँ, मतलब ये वेल डिफाइंड नहीं है बेसिकली, क्योंकि जहां तुमने ये फॉर्मूला लिख दिया सिर्फ बीटा लिख दिया, बट बताया
हाँ।
नहीं कि किस डायरेक्शन में बीटा को घटाना बढ़ाना है, क्योंकि ये जो रिजल्ट है फाइनली डायरेक्शन पे डिपेंड करता है। तो इसलिए सिर्फ ये लिखने से इट्स नॉट अ वेल डिफाइंड फॉर्मूला। ओके,
But sir,
so therefore
same
we have
goes
to
with
do it in the way we are doing here। हाँ, अब बोलो, अब क्या बोल रहे हो?
sir, same goes with eta, because eta is also not well defined. We are just
नो, ईटा इज नॉट लाइक दैट। ईटा हम लोग पहले शुरू में प्रेस्क्राइब करेंगे व्हाट इज ईटा, एंड देन वी टेक द डेरिवेटिव।
तो बीटा भी वैसे प्रेस्क्राइब करके नहीं हो सकता।
नहीं तो क्या बीटा क्या प्रेस्क्राइब करोगे?
मतलब जैसे ईटा मान लीजिए हमने कुछ डिफाइन किया, अल्फा ई कैप प्लस बीटा जे कैप प्लस गामा के कैप
अब
टाइप का।
अगर तुमने बीटा प्रेस्क्राइब ही कर दिया, तो फिर लिमिट कैसे लोगे बीटा गोइंग टू जीरो मैग्नीट्यूड?
अच्छा, हाँ ठीक है।
नहीं ले पाओगे ना। वहां जो ऊपर के फॉर्मूला में ईटा प्रेस्क्राइब करने का मतलब ये नहीं है कि एप्सिलॉन प्रेस्क्राइब हो गया, हम लोग अभी भी एप्सिलॉन टेंडिंग टू जीरो कर रहे हैं, बट यहाँ पर तो चेंज ही नहीं कर पाओगे फिर बीटा को, अगर तुमने बीटा प्रेस्क्राइब किया तो।
सर मतलब इस टाइप से रख ले, मेरा मतलब है कि अल्फा टाइम्स आई कैप प्लस जे कैप प्लस के कैप, इस टाइप से रख लिया, और फिर लिमिट अल्फा टेंड्स टू अल्फा बाय √3 अल्फा टेंड्स टू जीरो हो जाएगा, अल्फा टेंड्स टू जीरो हो गया वो।
बट दैट्स अ वेरी स्पेसिफिक केस। उसमें तुमने ये जो है सिर्फ उसी डायरेक्शन के लिए लिया जो कि अलोंग आई प्लस जे प्लस के है। अगर मुझे कोई और डायरेक्शन के लिए करना होता तो क्या करते?
सर तो मैं उस वेक्टर को इसी हिसाब से एडजस्ट करता हूँ, उस यूनिट वेक्टर को जो
तो
अल्फा के
बात
साथ
तो
है।
वही हो गया ना, तो फिर बात तो वही हो गया फिर जो मैं यहाँ पे कर रहा हूँ। यही तो फिर तुम बोल रहे हो, तुम जो कह रहे हो फिर तो वही बात हो गया।
Okay.
All right, so let us see where we were. So basically we understood here the idea of directional derivative. अब ये देखो, when I come back here, as I told you, this delta x could be, you could write it as y or you could write it as eta. All right, हमें इसे सिर्फ डेल्टा x ही लिखने का जरूरत नहीं है। Now coming back to taking the derivative with respect to vector. So I was saying, how do I define this del f by del x? So I said that define it in the following way: limit epsilon tending to 0, f of x well, I can't define it like this. Let me first write it what I mean here. So this is f of x plus epsilon, एंड सपोज को यहाँ पे हम लोग ईटा ही लिखते हैं, ठीक है, एक्स प्लस एप्सिलॉन ईटा माइनस एफ ऑफ एक्स divided by epsilon. So we just learned that this is directional derivative along eta, directional derivative along eta, and we write this as del f over del x dot with eta, इस तरह से लिखते हैं। तो बेसिकली जब लेफ्ट हैंड साइड को वर्कआउट करोगे और उसको अगर इस फॉर्म में लिख पाए तो डॉट इटा छोड़ के जो भी मिलेगा वो हो गया हमारा डेल एफ बाय डेल एक्स। कैन यू अंडरस्टैंड व्हाट आई एम सेइंग? तो हमारा प्रॉब्लम ये था कि हमें ये पता नहीं था कि डेल एफ बाय डेल एक्स कैसे करेंगे। We didn't know how to do it. तो हम लोगों ने क्या किया, ये लेफ्ट हैंड साइड पहले किया, एंड दिस वी कैन ऑलवेज डू इट, क्योंकि यहां जो डेरिवेटिव ले रहे हैं एप्सिलॉन के रिस्पेक्ट में ले रहे हैं। ओके, सो दिस इज बेसिकली डी एफ एप्सिलॉन बाय डी एप्सिलॉन, ये है वो। और स्केलर के साथ डिफरेंशिएट करना हमें बहुत अच्छे से आता है। अब ये जो फाइनल डिफरेंशिएट करने के बाद जो भी आएगा एक्सप्रेशन, उसको हम लोग इस तरह से लिखने का सोचे, ईटा को अलग करने का सोचे, तो जो बचेगा वो हो गया हमारा डेल एफ बाय डेल एक्स, उसको हम लोग बोलते हैं डेल एफ बाय डेल एक्स। लेट अस सी थ्रू एन एग्जांपल, मे बी दैट विल हेल्प अस। सो सपोज करो एफ ऑफ एक्स को हम लोग लेते हैं 2x, ऑलराइट, सॉरी ये 2x तो ये वेक्टर नहीं है ना, स्केलर फंक्शन है, सो आई विल टेक इट एज 2x डॉट x, ये ले लेते हैं 2 times x dot x. So because f is a scalar function, this is equal to 2 times x dot x. Now I want to know what is del f by del x. So as I said you above, this is what I have to do. So I will first evaluate f of x plus epsilon eta minus f of x, then divide by epsilon and take the limit epsilon going to 0. And I can do it perfectly because यहाँ हम लोग न्यूमरेटर में स्केलर है, डिनोमिनेटर में भी स्केलर है, सो वी नो एवरीथिंग. So this is then equal to 2 times x plus epsilon eta dot with x plus epsilon eta minus 2 times x dot x divided by epsilon. Okay, और इसमें लिमिट लेना है epsilon going to 0. So this is then equal to, now we know how to do this dot also, right? So this is then 2 times x dot x plus 2 epsilon x dot eta, correct? Plus epsilon square eta dot eta. Is that fine? And then you have this minus x dot x also. And this has to be divided by epsilon. And then I have to take the limit epsilon going to 0. So you see, everything is perfectly fine. Then I subtract these two, it goes away. And this then becomes limit epsilon going to 0. 2 times x dot eta plus epsilon into eta dot eta, which is then equal to simply 2 times x dot eta. Okay, so this is the left hand side, और हमें इसको equate करना है with del f by del x dot with eta. So can you now see what is del f by del x? Anyone?
2x.
2x, right? So del f by del x. So this is what I said. How to get del f by del x? हम इसको डायरेक्टली नहीं निकाल रहे हैं, क्योंकि डायरेक्टली पता नहीं है ना कैसे डिफरेंशिएट करते हैं वेक्टर के रिस्पेक्ट में. So what we did is we simply scalarized the differentiation in this way and then compared it with the right hand side. To extract what is del f by del x.
तो RHS कैसे मिला?
सॉरी, RHS कैसे मिला वो उसका
हाँ.
अच्छा, ये भी बहुत अच्छा क्वेश्चन है कि RHS को हम लोगों ने ऐसे ही क्यों लिखा है. कैन एनीवन मेक अ रिमार्क हियर, ऐसा क्यों लिखा है इसको?
Which one?
सत्येंद्र प्रताप सिंह. एनीवे लेट मी से दिस. देखो, अगर ये ऐसा होगा तो इसको हम लोग क्या लिख सकते हैं? सबसे पहला बात कि अब जो है del f by del x का क्या मीनिंग है. लेट मी नाउ से दैट जब भी किसी फंक्शन को किसी वेक्टर से डिफरेंशिएट करते हैं तो उसका जो कॉलम फॉर्म होगा ना, उसमें हमें उस फंक्शन को उस वेक्टर के कंपोनेंट से डिफरेंशिएट करते जाना है. तो इसका मीनिंग सिंपली यही है कि ये हो गया del f by del x1, del f by del x2 और del f by del x3, and then dot with eta 1, eta 2, eta 3. ये हो गया. So finally this is del f by del x1 into eta 1 plus del f by del x2 into eta 2 plus del f by del x3 into eta 3. Now can you see why it should be, why the left hand side should be equal to this right hand side thing? Any idea? देखो लेफ्ट हैंड साइड में क्या हो रहा है. आई थिंक हम लोगों ने ऊपर में भी किया हुआ है. यू सी दिस इज व्हाट इट इज नो हियर. यही चीज नीचे लिखा है ना मैंने, h के जगह पे बस एप्सिलॉन करना है, कॉम्पोनेंट वाइज जो लिखा है. Okay, if you are not convinced, then let me do it again. I'll do it again, no problem. So the left hand side was limit epsilon tending to 0, f of x plus epsilon eta minus f of x divided by epsilon, okay, which is same as limit epsilon tending to 0, f of x1 plus epsilon eta 1 comma x2 plus epsilon eta 2 comma x3 plus epsilon eta 3 minus f of x1 x2 x3 divided by epsilon, okay. And so I can also write this as limit epsilon tending to 0. न्यूमरेटर में अब देखो ये टेलर्स एक्सपेंशन लगाते हैं. So can I write this as f of x1 comma x2 comma x3 plus del f by del x1 into epsilon eta 1 plus del f by del x2 into epsilon eta 2 plus del f by del x3 into epsilon eta 3 minus f. वेल टेलर्स एक्सपेंशन में और भी आगे भी जाएगा, बट वो सब एप्सिलॉन स्क्वायर वाले टर्म्स होंगे, राइट. एप्सिलॉन स्क्वायर एप्सिलॉन क्यूब वो सब होगा, और लास्ट में माइनस एफ करना है, और यहाँ पे डिवाइड बाय एफ है, डिवाइड बाय एप्सिलॉन है. तो ये एफ और ये लास्ट का एफ कट गया, और ये देखो ये एप्सिलॉन यहाँ पे इन सबों से कट गया, और ये एप्सिलॉन स्क्वायर जो है ये एप्सिलॉन बन गया, फिर एप्सिलॉन क्यूब जो है वो एप्सिलॉन स्क्वायर बन जाएगा. और जब तुम लिमिट लोगे एप्सिलॉन टेंडिंग टू 0 तो वो क्या होगा, दैट्स सिंपली del f by del x1 into eta 1 plus del f by del x2 into eta 2 plus del f by del x3 into eta 3, okay, which is what I had seen above, right. This is what you had here, see, and therefore I could write the right hand side the way I have written here. But you don't have to come through component wise. This is more philosophical. I could directly write what I have written on the right hand side, because what is happening on the left hand side? On the left hand side, you are changing the argument of x. Can you see? You are changing the argument of x. Sorry, I am changing the argument of the function f, and the argument is x. So I am changing the argument x in the direction of eta. Therefore, what I will get is the derivative with respect to x in the direction of eta. Now it is because in the direction of eta, therefore it has to be dotted with eta. Okay, so this is more philosophical here, that I could directly write this. And in fact, in this way, you could also think of taking derivative with respect to second order tensor or third order tensor or even higher order tensor. Suppose you have a function f which depends on a second order tensor a. Okay, and I want to see what is del f by del a. I want to know what is this. Then a way to get this is you simply evaluate this. Sorry, I can't write here. Yeah, limit epsilon tending to 0 f of a plus epsilon into some b minus f of a divided by epsilon and equate it to del F over del A and double contraction with B. So left hand side you evaluate it and write it as some tensor double contracted with B, whatever is here. Then that sum tensor is your del F by del A. See, what is the meaning of double contraction? It is simply del F by del Aij into Bij. So basically you take the derivative along with respect to component Aij and multiply with Bij. And why I'm doing it here? Because you see, when you are writing this, you are changing the component Aij by epsilon into Bij. And you are taking derivative only with respect to epsilon. Therefore, you get this del F by del Aij into Bij on the right hand side. I hope you are understanding what I said.
Yes, sir.
Anybody could not understand? Nomen Tomar?
Yes, sir. It's okay. I'm able to understand, sir.
Okay, that's very good. All right, so this is how you can take the derivative with respect to vector, with respect to second order tensor, third order tensor, fourth order tensor, or any order tensor. So let's get back to gradient thing that we had earlier. So gradient. So gradient we define like this: gradient of f using the fundamental theorem would be simply limit epsilon tending to 0, f of x plus epsilon into eta minus f of x divided by epsilon. And the left hand side is actually gradient of f dot with eta. So that's how you can extract gradient of f. And you can do gradient of a second, third, fourth, any order tensor. And the way it is defined is the following. You say gradient of anything here. That's del f, sorry, del of not f, it is the thing that is here. So del of the thing which is here with respect to del xi tensor product ei. So this is the definition for gradient. Okay, and this works or this matches with when this dot is scalar. See, in case when dot is scalar, so when this equals f, then gradient of f is del f by del xi into ei. Okay, and this is what we had said earlier also. No, this is the definition of gradient also. But this we could see just for scalar. Now we can use this formula to obtain gradient of even a vector. For example, gradient of a vector f, that is now equal to del of f divided by del xi tensor product ei. And if you expand your f in terms of ei, ej, then you could also write this as del of fj, ej with respect to del xi tensor product ei. And if E1, E2, E3 are not changing with x1, x2, x3, for example, in case of Cartesian coordinate system, E1, E2, E3 is fixed. So in that case, this becomes del Fj over del Xi of Ej tensor product Ei. Okay. So basically, gradient of F is now a second order tensor. And the matrix of this gradient in E1, E2, E3 is simply del Fi over del Xj. Are you with me? Okay, no problem, right? This is perfectly fine. Likewise, you can do gradient of a second order tensor also. For example, you can think of gradient of sigma, where sigma is Cauchy stress tensor. I think some of you must be knowing about Cauchy stress. I think all of you know about Cauchy stress, and you also know that it's a second order tensor. So इसका अगर gradient लेना हो तो क्या होगा? That's simply del sigma over, let us say, del xk tensor product ek. And if you expand sigma in terms of its components, then it is del over del xk of sigma ij into ei tensor product ej tensor product ek. So it's a third order tensor. And in the matrix form, well, it's not a second order matrix, it's a third order matrix. Or you could also say it's a three-dimensional array, for example. So this is del sigma ij over del xk. And bottom line is that gradient increases the order of a tensor, because you see, when the gradient acted on a scalar, it became a vector. When the gradient acted on a vector, it became second order tensor. When the gradient acted on a second order tensor, it became a third order tensor. All right. Any problem with gradient? No problem. All right. So if there is no problem, then we'll go to second operator, which is called divergence. So all of us have seen divergence of a vector, for example, in our first year mathematics course. So divergence of a vector v, for example, we used to write it as del v1 by del x1 plus del v2 by del x2 plus del v3 by del x3, isn't it? But now we'll see that we can do divergence of not just a vector, but also of a second order tensor or third order tensor or fourth order tensor. And it is the following. So divergence we denote by that gradient symbol, but then there is a dot also. So this is the divergence symbol. And divergence of anything, let us say cross. So that's equal to del of that thing with respect to, let us say, xj, and then it has to be dotted with ej. See, in the tensor product, this thing was tensor product, but now it's a dot product. It's a dot. Okay, let us see what happens if x is a vector. Can we recover this formula? So let us see that. So divergence of a vector v. So this is del v over del xj dot with ej. Now let me expand this v, so it becomes del vi over del xj of ei dot ej, which is simply del vj by del xj. Okay, and this is what it is here, right? You can likewise do divergence of a second order tensor. In your solid mechanics course from undergraduate, or if you have done continuum mechanics, some of you have done it, then you would have seen that the equation of equilibrium, that is divergence of sigma plus the body force is equal to density times acceleration. So that's the tensor equation of equilibrium. इसी को कॉम्पोनेंट में लिखोगे तो ये बहुत बड़ा हो जाता है, बट ये टेंसर फॉर्म में काफी कॉम्पैक्ट इक्वेशन है. So basically this equation has got this divergence also. And how it is defined? Well, we have just seen how to do divergence. Let us see what happens to it when you take divergence of a second order tensor, that is sigma here. So divergence of sigma based on our formula is del by del x. It's a k of sigma dot with ek, isn't it? So this becomes del sigma ij over del xk ei tensor product ej. Remember that this ei ej thing came out of this bracket because it is not changing with xk. But if it were changing with the coordinate, then you will also have to take the differentiation of the basis. Can you think of an example where the basis vectors change with coordinate? Anybody can think of an example of a coordinate system in which the basis vectors are changing with coordinate? So in Cartesian coordinate system, the coordinates are x1, x2, x3, and the basis vectors are I, j, k. And as you change x1, x2, x3, I, j, k remains the same, they do not change. Is there any coordinate system in which the basis vectors change?
Sir, every curvilinear coordinate system in the basis.
Curvilinear coordinate system, yes. And more specifically, cylindrical coordinate system, where you have er, e theta, ez, and the coordinates are r, theta, z. So as you change theta, er and e theta also changes. Okay, so when you're taking the divergence with respect to cylindrical coordinates, then you can't take this ei and ej out of the bracket from here. All right. So anyway, so right now we are focusing on this Cartesian coordinate system. So we have this thing, and it has to be now dotted with ek. So this becomes del sigma ij over del xk, and the way it is going to act is whatever is in the extreme right and the dot thing, so you have to dot them. So it becomes ei delta jk, which is del sigma ik over del xk ei. So you see what is this finally? It's divergence of sigma is now a vector. And what's the component? That is del sigma ik over del xk. The ith component is del sigma ik over del xk. So divergence basically reduces the order of a tensor. Because you see, second order tensor became a first order tensor. When you do the divergence of a vector, it became a scalar. Okay, so this is about gradient and divergence. Likewise, you can also think of curl. So you can think of curl of a vector. So till now I have only seen curl of a vector. I haven't seen curl of a second order tensor or third order tensor. I have only seen curl of a vector, and this is something you are already aware with. I have discussed this also, so I'm not going to discuss this further. Okay, then you can have some more interesting thing. For example, Laplacian. So Laplacian of a, you can have Laplacian of anything. And what is Laplacian? So let us say, so Laplacian, it is the following: divergence of gradient of the thing of which we want the Laplacian. So this is the Laplacian, divergence of gradient. Okay, not the gradient of divergence, but divergence of gradient. Suppose I want to do the Laplacian of a scalar quantity, f. And Laplacian is, this whole thing is then given by this triangle, which is not inverted. So Laplacian of this. So as you can see, Laplacian does not increase the order of a tensor, because we have to first do gradient, which will increase the order, but then you have to do divergence, which will decrease the order. So overall, the order does not change. So I can write here, it does not change the order. So suppose I want to do Laplacian of a scalar function f. So by definition, I have to do divergence of gradient of f. So now let us use the formula. So divergence of gradient. So gradient is del f over del x j ej, and then I do divergence, then it becomes del 2f over del xi del xj ei dot with ej, isn't it? Which is del 2f over del xi del xj delta ij, which is del 2f by del xi del xi. Okay, and you must have seen that this is the Laplacian. If you write it in the, if you expand it fully, then it is del 2f by del x12 plus del 2f by del x22 plus del 2f by del x32. So this is the Laplacian, right, that you have seen. You can likewise do Laplacian of a vector quantity. So let me see what is that coming out to be. So suppose I want to do Laplacian of a vector v. So Laplacian of v. So by definition, it is divergence of gradient of v. So this is same as divergence of del vi over del xj ei tensor product ej, which is equal to del 2 vi over del x j del x k ei tensor product ej, and then it is dotted with ek. So this becomes del 2 vi over del x j del x k of EI into delta JK, which is same as del 2 VI over del XJ into del XJ of EI, right? So that's the definition. Or you could also see this is same as VI comma JJ. Okay, so comma, so this is a notation basically. If you write something after comma, that means you have to take the derivative. EI. And you can also see that it's same as del 2 of the vector V itself over del xj, right? Because Vi and Ei, you can bring them together and it becomes a vector V. So this is also V comma JJ. Any question here? Please ask me. Anybody? Everybody is fine? Nobody has got any problem? Are you guys there? Somebody please say something.
Sir, we are following.
Yes, sir, we are listening.
Okay,
It's okay,
thank
sir.
you. Let me increase the time also because it's almost going to be over. Sorry, I don't want to exit. I have to increase, extend. Okay. So, all right. So that was Laplacian. And there are, likewise, there are several things. But let's do what is now called Gauss divergence theorem. That's also a very important thing. So till now we talked about differentiation. We'll now talk of integration. And one of the most useful integration theorem is Gauss divergence theorem. So this can be used to convert a volume integral into surface integral. So for example, think of a body and any point here is given by, let's say, x. Any point in the body is given by x. And there is a vector field, let's say V. At every point in the body. So there is a vector field defined over the body. All right? And suppose the outward normal here is n. So the body I'm going to denote by omega, and the surface of the body I'm going to denote by del omega. Okay, so what this Gauss divergence theorem tells us is that volume integral of divergence of the vector field that's equal to surface integral of that vector dotted with n dA. Okay, so this is the Gauss divergence theorem written in tensor form. Are you all with me? Of course, there is a proof to it also, but I'm not going to prove it. But I will deduce several interesting results from here.
Sir?
Yes.
Sir, why del symbol is used? Like any specific intention, or means because it has
Well,
partial
this is how,
derivative meaning?
yeah, this is how mathematicians do it. So that we are just following mathematicians.
So,
They use del to denote the boundary. If the domain is omega, then if you put a del beforehand, it becomes a boundary. So in this case, it's a 3D body and the boundary is the surface. If the body were, just a planar thing that you see on the paper, if the body were a plane or an area, then the boundary would be this line itself, the bounding line. And then again, they denote by del omega. So they put del in front to denote the boundary.
okay.
Okay. So any other question? So you see
Sir,
here, this, yeah, please.
sir, that outward normal is it a unit vector?
Yes, that's a unit vector. It's a normal, it's a unit vector. Very good. And you see, it is
Thank
so
you.
interesting. You have a volume integral and you are able to convert it into a surface integral. Likewise, if you have a surface integral, you can get back to volume integral. You may not be able to appreciate it now, but later on you will see there will be so many derivations where you will use this theorem, like anything. All right? So should I go ahead? Now, using this, I want to see what will be integral over del omega of a scalar function phi into n dA. Can I use Gauss divergence theorem here? Anyone? What do you think? Can we use Gauss divergence theorem? Look at the Gauss divergence theorem. Is it in that particular form? So I can compare this with the right hand side here. But on the right hand side, I have a vector field V dotted with n. So V is a vector field. But here in this integral, I have a scalar field phi multiplied with n. So it is certainly not of that form. But we can do a trick here. So instead of finding this, let us do the following. Why don't we find out this thing? Phi n dot an arbitrary vector A dA, where A is constant but arbitrary. Okay. Now, actually the first step was I would do this integral over del omega phi n dA dot with A. So I'm starting from here, starting point. You see this A is arbitrary but constant. So because A is constant, I can bring it inside the integral. So it comes inside the integral and this is what it becomes. Okay, are you with me? Now this I could also write as integral over del omega phi A dot with n dA. Isn't it? And now you see this is in the form of Gauss divergence thing here. Because now the vector field is your phi A. Phi A is the vector field. So when you apply Gauss divergence theorem, it becomes integral over omega of divergence of phi A dA. Correct? Now let us see what is divergence of phi A. So I'll do it here. So divergence of phi A. Should I increase the time? Are you guys
So that
okay?
that will be
Increase the time?
d.
dv.
So d.
ये
Yeah, okay, this is dv. Yes, this is dv. Should I increase the time? तो तुम लोग कोई कुछ कह नहीं रहे हो.
No
इसका
problem, sir.
मतलब
No problem, sir.
okay, let
No
me just
problem,
increase
sir.
by 10 more minutes. उसके ज़्यादा मैं नहीं करूँगा. So here I go. Okay. अब इसको हम लोग वर्कआउट करते हैं क्या होगा डाइवर्जेंस. सो वी नो दिस इज डेल ओवर डेल एक्स जे of phi A dot with EJ, isn't it? So this is del phi over del x j A dot EJ, which is simply AJ, correct? And can you see that this is also same as gradient of phi dot with A? Do you think it is the same thing? Right? So this thing is basically this thing over here. So let us now substitute it back here. So this becomes integral over omega gradient of phi dot with A dv. But again, because A is constant, it comes out of the integral gradient of phi dv dot with A. Okay, and now you see in this entire step A was arbitrary, right? Sorry, I'm not able to go down for some reason. What's happening? Okay, there's some problem. Yeah. Now let us compare the first step and last step. Compare these two. Since A is arbitrary, what do you think? What can we write? The thing inside the bracket in the first step and last step must be the same, isn't it? Because A is arbitrary. So this simply implies that integral over del omega phi n dA is equal to integral over omega gradient of phi dv. Okay? Likewise, you can think of another very nice thing. What if you have integral over del omega of V tensor product n dA? Can we convert this into volume integral? So obviously we have to think of Gauss divergence theorem, but it is not in that particular form because Gauss divergence we need it as V dot n. So what do you think? Can we do it? So yes, of course we can do it. The idea is the same. Dot it with a vector A, arbitrary vector A, and then bring it inside. So what does this become? This becomes integral over del omega A dot V into n dA. Okay, and now you see A dot V is like a scalar function, and so you can use the previous formula here. So A dot V, think of it as phi, And so this becomes integral over omega of, okay, I think I made this mistake here. This is, gradient is here. So this is now gradient of A dot V dV. So now we have to work out this gradient of A dot V. So let's work it out. Gradient of A dot V. So what do you think? What is this equal to? A is a constant. Okay. You know, many people make a mistake and simply say this is equal to A dot gradient of V, because A is a constant, take it outside of the gradient. But this is not correct, because you see A is a vector and then grad V is a second order tensor. How can you dot a vector with a second order tensor? So don't make this mistake. So let's do it methodically. So this is now del by del xj of AI Vi, right, into Ej. So this is same thing as del Vi over del xj into Ej into AI, right? Okay, now what can we do? Any idea what can we do now? See, I want to write it as something into A. I want to take that A outside. It becomes equal to grad V into A. And so we can finally come back here and write this as integral over omega grad V dV into A. Okay, and then when we compare, then this thing inside the bracket, what we get is integral over del omega V tensor product N dA is equal to integral over omega grad V dV. Yeah, that is it. All right. Any query here? I think I didn't show the full step. You work it out and you'll get it. Maybe, you know, I leave it to you as an exercise. So that's the Gauss divergence theorem applied to vector field or scalar field or a tensor field. You can apply it to anything, but then you have to do these tricks. And final is what's called Stokes theorem. This is also a very beautiful theorem, and it is often used in fluid mechanics and also in electrostatics, for example. So what does this say? So think of a surface. So this is surface, not a 3D body, it's a surface. And let's say I denote the surface here by omega. So you see surface is omega here. Earlier omega was volume, but now your surface is omega. And the bounding curve, that's del omega. See, this surface is a 3D surface. It's not in just a plane. It's a 3D surface. So you take a paper and you and you cramp it, you get a 3D surface. So that is the surface, and then the boundary of the paper, that's del omega. Okay, and the Stokes theorem says, so of course it relates the integral over surface to integral over the boundary, and it is simply, it says that curl, so that is del cross V, okay, just a second, I'll just check it. I think I'm making a mistake here. Yeah, so it is indeed curl del cross V dot N dA. Okay, del cross V dot N dA. That is equal to, and what is N here? N is the surface normal. Okay, N is the surface normal. And let us think of this T here, tangent to the boundary. This is equal to V dot T dl, where dl is the small element along the boundary curve, and T is the tangent. Also notice here that this surface, it's an open surface. It's an open surface. It's not a closed surface. Unlike the surface in the Gauss divergence theorem, so the Gauss divergence theorem surface here, because this surface was encompassing a volume, so therefore the surface here is closed. It's a closed surface. So I'll just make a remark here. It's a closed surface. But here it's an open surface. But the boundary to this open surface is of course a closed curve. So this is a closed curve. All right. So curl of a vector field, curl of V dot with N dA is this integral. And you know, a very interesting thing about this Stokes theorem is that you see this boundary curve del omega, you can have same boundary curve for a lot of surfaces. You think of another surface which is just above this surface, but bounded by the same curve. Isn't it? You can think of so many surfaces which shares the same boundary del omega. So what this theorem tells me is that right hand side is always the same, but the left hand side is changing because the surface is changing. But the theorem says it does not depend on surface. So for any omega, encompassed by del omega, you get the same value. This is what Stokes theorem says, because the right hand side is independent of the surface, right? So for any omega encompassed by a given del omega, the surface integral will be the same. Okay, so I hope, so I will stop here. And as I said to you, this is from the chapter 5. You please go to chapter 5 and work out all the solved examples. There are so many interesting solved examples there. Work out all the solved examples. Okay, now if you have any query, please ask me. We have 3 minutes left.
सर टी का डायरेक्शन कौन सी डायरेक्शन में लेंगे?
T.
Yes.
T is tangent to the boundary of the curve.
दो डायरेक्शन हो सकते हैं।
अच्छा वो okay, so we have to go anti-clockwise. As we go along the boundary, the surface should be to the left of us. As we go along the boundary, the surface should lie to the left of us, not to the right of us. So that's the direction of T.